Okay. So I'm going to be talking tonight about radio propagation, particularly in regards to a particular part of the radio frequency spectrum and how that's affected by space weather and particularly what's happening on the sun. So my subtitle here is How the Sun's Activity Affects Radio Transmissions on Earth. So what my talk is going to cover is, first of all, I'm going to introduce the radio spectrum a little bit, talk about what the radio spectrum is. And from there, we're going to zoom in on a particular part of the radio spectrum, which we call shortwave radio. And then from there, we're going to talk about the ionosphere, so the charged layers in the atmosphere and how they interact with radio propagation. Then we're going to talk about the solar cycle and the ionosphere, so how what's happening on the sun affects what's happening in the ionosphere and therefore how that affects radio transmission. And then I'm going to touch on some of the effects of solar events on our technology on Earth. I will also have a little science experiment for you to participate in if you want to as well. So, okay, so let's start. Radio is another electromagnetic spectrum, just like light. Okay, so we look at light and we measure its wavelength in nanometers. So we know that 400 nanometers is almost ultraviolet, down to 700 nanometers, which is deep red. Anything below that, longer than that, is infrared. And of course, we'll know the astrophotographers among us will know the special line at 656 nanometers. Hydrogen alpha, of course. So how big is a nanometer? 10 to the minus 9 meters, or a millionth of a millimeter. So red light, its wavelength is really small, 0.0007 millimeters in wavelength. Okay, now, the reason I'm talking about the wavelength of these electromagnetic radiations is because in radio, our wavelengths that we're dealing with are much longer than light. So generally around 10 millimeters to around about 3,000 meters or so is the wavelength of radio. Other than that, it's an electromagnetic radiation, just like light. Okay, so a bit of a physics lesson here. With light, we tend to think of it in terms of its wavelengths in nanometers. With radio, it's more useful to think about it in terms of its frequency. And so how do we translate the two? So we've got a wave represented here. And so all electromagnetic radiations take the form of a wave with one complete wavelength being represented there. Frequency, then, is just how many times that wave goes through a complete cycle. And we measure it how many cycles per second. So to convert wavelength to frequency, we need the very foolish Y, and I'm guessing by the giggle that I just heard, somebody knows what that means. This was a trick that my physics teacher in the sixth form way back in 1987 taught me, and I remembered it, so it worked. Okay, it's this little triangle of formulas here. V is our velocity, which in this case, electromagnetic radiation, it's always the speed of light. So 3 times 10 to the 8 meters per second, near enough. Our frequency is in cycles per second, and our wavelength, lambda, in meters. Know any two, and you can work out the other one. Very simple. Velocity over wavelength is frequency, velocity over frequency is wavelength, frequency times wavelength is you get it. Okay, you know how this algebra stuff works. Why do we call it a very foolish Y? Because it's a Y that's standing on its head. Right? That was my sixth form physics teacher taught me that. And it worked. He had a great thing for mnemonics for formulas. Okay, so as I said, you know any two, and you can then, from that, you can work out the other one. Velocity divided by wavelengths. Frequency, higher frequency equals shorter wavelength. Right, so with that in mind, like I said, we usually talk about radio waves by frequency, not by in terms of wavelength. It's not strictly true. People do sometimes talk about bands by wavelengths, but normally radios are in frequency. The unit of measure is hertz. So 1 hertz is 1 complete cycle per second, which means 1 kilohertz is 1,000 cycles per second, a megahertz is 1,000,000 cycles per second, a gigahertz is 1,000,000,000 cycles per second. You get the idea, right? And for those of you who are above a certain age in the room, you'll remember radio dials when they looked like this, and you actually had the pointer which slid across, and these numbers here. Okay, so your AM band, there's your kilohertz, and your FM band, there's your megahertz. Okay, so all you're doing is just selecting a frequency on the radio that the channel is that you're going to listen to. So from 2 slides ago, when I said radio goes from around 10 millimeters to around 3,000 meters, so that's around 30 gigahertz down to 100 kilohertz. It's a bit of a soft limit, really, because there are some specialized uses for the radio spectrum outside of those limits, but the vast majority of use of the radio spectrum happens within those areas. Okay. Now, we know that different wavelengths of light behave differently. And the way they behave differently is we perceive them as a different color. Different wavelengths of radio also have different behaviors. They're stopped by certain things. They behave different ways. They interact with the atmosphere in different ways. And so different bits of the radio spectrum are used for what they most lend themselves to. So AM radio is quite low in frequency. FM radio is higher, 88 to 108 megahertz. And then you've got your Wi-Fi and your Bluetooth and so on. And then you've got satellites, which operate. Your Sky TV satellite usually operates around, I think, 12 gigahertz or something like that. Okay, so I'm a big Star Trek fan, so I had to put some Star Trek in here somewhere. Okay, so when you're watching Star Trek and they say it's EM band radiation, Captain, that's what we're talking about. So this is our entire electromagnetic radiation spectrum. And you can see we start with these gamma rays and cosmic rays and so forth. These are the things which have these really high energy levels, bigger electron volts and peta-electron volts that Anne was talking about before. And then we come down to X-rays and then ultraviolet and then the visible light and then the infrared. And then here is our radio waves. And there's a whole spectrum of radio waves there. And there's those familiar numbers, kilohertz, megahertz, gigahertz, you see what they mean. And all the different things that are used in the radio spectrum are listed there approximately where they are. There's a huge number of uses for the radio spectrum. So this is not an exhaustive list at all. But what it does point out is that different parts of that radio spectrum are best used for different applications and different things. And the other interesting thing about them is that the lower you go in frequency generally, the greater range you get for your transmission, but the less information you can actually carry on that transmission, which is why satellites and so forth use high frequencies, because they carry a lot more information. Okay, so like I said, it was historically known that different sections of the radio spectrum behave differently. When we started playing with radio 120 or so years ago, the first race was to get a radio signal broadcast from one side of the Atlantic and be able to be received on the other side. So that was the first real big kind of test of making radio useful, making it something that would actually have some practical application. And what was discovered fairly quickly was that some radio signals would travel only locally during the day, but great distances at night. So this gave rise to some kind of concept that something was up there, was bouncing these radio signals back because they were transmitting over the horizon. And then there were other radio signals that behaved more consistently. They didn't do this bouncing, they were only purely line of sight. So before we had the internet and before we had satellites, we actually utilized this natural phenomenon. And because we found that it was, for the most part, quite predictable in terms of the way it behaved, these long-distance radio signals were used by radio stations to broadcast great distances internationally using a section of the radio spectrum we call shortwave. So prior to the internet, shortwave radio was actually quite a good cultural window into other countries and other cultures, because you could tune into radio stations from other countries. Okay, so for the curious, shortwave radio is generally regarded as being between the range of 3 to 30 megahertz. Okay, so the very foolish Y tells us that's around 100 meters down to 10 meters in wavelength. Now, within that shortwave radio spectrum, it's divided up into many different subsections for different usage. So broadcasting, amateur radio operators, signals, stations, relay stations, all that kind of thing. So everyone can take advantage of the different characteristics of the different parts of the shortwave band. And this here is radio enthusiasts, what they call a Radio Shack. In the old pioneering days of radio, they used to make all their own equipment. But now you can just buy equipment like this with lots of knobs and plugs on it and hook it up and listen to radio stations from all over the world. And in the case of amateur radio operators, talk to them as well. But an older use of shortwave radio, here's something that I'm guessing is from the 1940s or 1950s or something like that. And you can see, this is really interesting. This radio, you see it breaks up the bands. So these different bands in the shortwave, and it even says here, I don't know if you can see down the back, morning, all day, afternoon and evening, afternoon, evening. So this radio kind of, the people who made this radio knew that certain parts of the shortwave were better during different times of the day. So this was a really popular thing in the old days before we could just go onto tunein.com or something on the internet and listen to whatever we wanted to. Now, what's this dude got to do with radio? So the interesting thing, as I mentioned before, was that radio signals behave differently. It was discovered that shortwave radio signals behave differently at night than during the day. And you can tell me what this line here is called. Here's a hint. There you go. Exactly. The interesting thing is the radio propagation characteristics change along the terminator. So if you're trying to do a broadcast to somewhere, you need to know where that terminator is in relation to yourself and the person you're trying to broadcast to, and vice versa. If you're listening to broadcasts, you need to know where that is. And of course, that's what the terminator looks like at this time of year, and in 6 months' time, it's going to look like that. Okay, so the path of the terminator is actually very different. So if you're a person who's using these shortwave radios, all of this has to play into your calculations in terms of what bits of the radio spectrum you're going to use to talk to what other places at what time of the day and year. So there's a bit more science to this than just tuning a radio and hoping you'll hear something. Okay, so this leads to this super nerdy habit that I'm talking about, which is called shortwave listening, or SWL for short. Because everything in radio has got a 3-letter code, absolutely everything. So SWLs, shortwave listeners. Of course, I used to indulge in this hobby, which is why I'm standing here talking to you about it now. And so the hobby is based on listening to these shortwave radio stations from around the world in different places and writing down about 15 minutes worth of details of what they were broadcasting. If it was a news bulletin, what were the stories in the news bulletin? What music did they play? That kind of thing. And you send that off to them, and they send you back one of these things, a verification card. And you can see it tells you what the frequency and the date and the time and confirms that you were heard that radio station. So this hobby, shortwave listening, is based on the collection of these verification cards. as I said, it is probably one of the nerdiest hobbies you can think of. But that's me. Right, so shortwave then and now. So as I mentioned, this is a bit of a trip down memory lane because shortwave was much more heavily used in the pre-internet era. It's kind of, the necessity for it has kind of passed a little bit now because you can get everything on the internet. But not always. It is still used for some broadcasting. It is still sometimes used for ship-to-shore communications. It can still sometimes be used for international phone calls. Amateur radio operators still use it. And also, polar research stations still use shortwave when they've got various conditions which make using satellite communications difficult. The interesting thing is, like I said, shortwave broadcast, actually broadcasting itself is still in use now, mainly by developing countries, and I'll come to why in a minute, but Radio New Zealand actually still has an international shortwave service. Always has had, they never shut it off. There's about 3 people that work on it now, dedicated, tireless people. They're probably all in their 50s and 60s by now, but you know. Shortwave is much less dependent on a distributed infrastructure than the internet. So in that sense, it is democratizing in terms of communications. Much more democratic. It only requires cheap equipment to receive it. I also want to talk just a little bit about numbers stations here, because this is one of the most fascinating things about shortwave radio. There's actually a link in here to a BBC story about them. So I can share that link afterwards. I can share this presentation afterwards. Numbers stations. These are radio stations that pop up at random somewhere in the shortwave spectrum, and somebody will read a series of numbers, just a series of numbers. And then as quickly as it popped up, it'll disappear again before anybody can actually track where the transmitter actually was. And nobody knows who is responsible for these number stations and where they're being broadcast from and what they mean. So there's all sorts of theories about these number stations. Mostly that they are connected with espionage or connected with foreign operators and embassies and that kind of thing, getting secret, untraceable messages from one part of the world to the next over an open broadcast medium using a code that nobody can understand or even know where it's coming from. So how cool is that? We're still doing that now in 2021. There are still number stations being broadcast right now. And it's literally a person reading a series of numbers into a microphone. So, yeah, there's a link there. You can follow that, and it takes you to a BBC story which talks all about them. I've actually heard numbers stations myself in the past as I've been tuning around the shortwave band. And as I mentioned before, that one should have been up there. Polar communications for regions outside satellite footprints, we use shortwave for that still too. So, you saw the old shortwave radio that I put up. This is what shortwave radios can look like today, just a little handheld radio with a little antenna on it there, or a little USB dongle. Screw the antenna in one end, plug it in the computer in the other end, and all the controls for the radio and all the knobs and dials and that are just on your computer screen. It's a software-defined radio. That's what shortwave radios look like now. Of course, to get the best out of them, you do need to plant this metal tree in your garden. But you can do so without it. It's just the bigger your antenna tree, the more distant and weak signals you can hear. It's exactly like a telescope. The bigger your telescope, the dimmer and the further objects you can see. Works on the same kind of principle. Okay, so much for shortwave. How does it work? What makes it go? What makes it bounce off the atmosphere and come back down to Earth and give us that international over-the-horizon propagation? Okay, we're talking here about the ionosphere, which, as the name suggests, is an ionized layer in the atmosphere. So what happens is the sun, the solar radiation, ionizes the gases in the atmosphere. So in other words, it cooks the gases in the atmosphere until they lose an electron or two. And what that does is it creates a sea of electrically charged particles in the upper atmosphere. That's what interacts with our radio waves. And these electrically charged particles will reflect some radio waves, let other radio waves through, and also absorb some radio waves as well. So we can call it a natural sky mirror for radio waves. So this is all very useful because before we had satellites, this is how we had over the horizon radio communication. Okay, now the reason that shortwave radio is so interesting is because these ionosphere charged particles work best with shortwave radio frequencies. Remember, I said 3 to about 30 megahertz. Okay, now let's drill down into the ionosphere a little bit and look in a little bit more detail, because it's not just one layer. The ionosphere is actually made up of several different layers. Each layer has specific properties which let some frequencies of radio through and absorb or reflect others. And then the layers change at night. They discharge, but at different rates. So you can see we've got this layer here, which is the D layer, that's closest to Earth. And then we've got the E layer, and then way up here, we've got the F layer. Somebody in the room may want to ask me, what about the A, B, and C layers? I don't know, and I haven't been able to find out why no A, B, and C layers in the ionosphere either. It's just one of those things that you don't question. So if anybody wants to find out and tell me, then I'll be happy to know. But what this does is it leads to the propagation of different radio frequencies being affected at different rates throughout the day and night as the layers charge and discharge. So a lot of study went into this, and I'm going to talk about these three layers. The D layer, it's the closest layer to the ground. It's made of ionized nitric oxide. So it's ionized by extreme UV, so 121.6 nanometer light. So that's very powerful, high energy ultraviolet, very short wavelength. But it disappears at night completely. Now, the interesting thing about the D layer is that it absorbs all these frequencies below about 10 megahertz. So nothing below 10 megahertz will bounce back to Earth from the sky during the day. Useful to know. Mechanism of action, lower frequency is a longer wavelength, which causes the electrons to move further, which means that more energy is required. Typically, we think of higher frequencies, more energy, but because the lower frequencies have got a longer wavelength, they have to move the electrons further, so they need more. A good analogy for that is, think of your subwoofer on your home theatre system. It's got a big, powerful amplifier in it because it's moving things a long way, even though it's low frequency. Okay, so just to hammer that idea home, it's like shining these low radio frequencies in the D layer. It's like trying to shine a red light through a blue filter. You're not going to get anything back. Now the E layer. This is the most interesting one. It's the middle layer. It's made of molecular oxygen. Again, it's ionized by the X-rays and extreme UV light from the sun. And it weakens, but it doesn't completely disappear at night. It also gains altitude at night. It reflects those frequencies that the D layer underneath absorbs. So there's a mirror up there and a filter over the mirror. The filter disappears off the mirror at night. So at night, the D layer disappears, the E layer gains high altitude radio mirror for low shortwave signals. There we go. And that allows for those lower band shortwave signals to have long distance reception. Finally, the F layer. It's the highest layer. It's, again, ionized molecular oxygen, and it's present day and night. It doesn't disappear, but it does split into two layers during the daytime, and it also gains a bit of altitude at night. It reflects everything, up to about 30 megahertz. The interesting thing is the top of the F layer is about the same height as the ISS, about 400 and something kilometers. And so if you're an astronaut on the ISS, or if you look at one of those videos from the ISS, how far those astronauts can see in either direction is about how far one radio hop would go from the top of the F layer. Now here's a practical experiment for you. If anybody wants to try this, you don't have to take my word about this radio propagation stuff. You can try this yourself. Okay, so if you came in a car tonight, when you get back out into your car, set your car radio to AM and tune it, assuming it's got a digital display, most of them do now, to 1080 kilohertz, 1080. Now, if you hear a signal, and you probably will, this is News Talk ZB, but 1080 is the Auckland frequency. Wellington's frequency is 1035. So if you go into your car, you turn it on to 1080, you hear News Talk ZB, all very nice, okay, leave the radio on 1080, come back tomorrow, morning, tea time, lunchtime, try again, turn it on to 1080, no signal. There'll be nothing there. And the reason for that is because Auckland is too far away for the direct path. The signal has to bounce off the ionosphere, but the D layer, which is present during the day, absorbs it, so the signal doesn't come back. At night, the D layer disappears, allowing the signal to reflect back from the E and F layers above, and you get your long distance reception of these lower frequencies. There is a disclaimer here. I don't necessarily endorse News Talk ZB. Mike Hosking alert, okay? So just, it's just a handy frequency that you can try this experiment with. So give it a go and let me know if you are successful with it. You probably will be. And in fact, I can give you some radio frequencies of some other radio stations you can listen to. Even on the other side of the Pacific Ocean, you can listen to medium wave AM band radio stations from all the way from North America. Okay, so let's put it all together. Here is my lovely graphic of the ionosphere day and night. So you can see we've got the E region and the F region at night, and we've got the D, E, and F1 and F2 regions during the day, and in between the two, well, there's Arnie. Right, so now we talk about how all this affects the radio propagation. So the most predictable daily cycle happens at shortwave frequencies. It's predictable, it's known, and it can be used to great advantage in programming how you're going to transmit to what part of the world at what time of the day. Frequencies below about, well, I said 10 before and I've said 7 here, won't bounce off the atmosphere during the day. It's been my experience playing with the stuff that 10 megahertz, it's more like 7 really. Okay, so at night, that section of the band is very busy because you've got millions of stations from all over the world where it's dark between you and them, coming back, and sometimes they sit on the same channel as each other and they interfere with each other. These bands are equally good for distant propagation, day and night, and above this frequency or so, it's better during the day. So, like I said, it's helpful to know where the terminator is. What direction can you expect to hear what frequency of broadcast from? And of course, the guys who are doing amateur radio, they're actually transmitting to each other on these frequencies. That's useful for them to know as well. And this being 2021 and the internet being a thing now, apparently, there are now live websites which are crowdsourced, which have got radio receivers that are feeding this crowdsourced thing all over the world, listening to channels, matrixing into this big computer algorithm, which is then predicting over different parts of the world what the highest frequency is that will bounce off the atmosphere and give you a signal. And you can go to that. There's a website down there. You can go to that and pick anywhere in the world and go in real time and see what the current shortwave radio propagation characteristics are. We didn't have this when I was playing around with shortwave radio because the best computers we had then were these Commodore 64s, and so they were not quite up to this kind of thing. Okay, now let's actually bring this relevant to astronomy, seeing as that's why we're here. Okay, so the sun actually affects all of this stuff in quite a significant way. So we know that the sun has approximately an 11-year cycle. In actual fact, it's observed to be anything from 9 to 14 years. But when we have solar minimum, there are no sunspots visible on the sun. And when we're at solar maximum, there are lots of sunspots visible, and the sun's magnetic activity increases, and that gives us all sorts of coronal loops and solar flares and all those other things that the sun likes to throw at us. We first observed the solar cycle in the 1700s when we started to explore the universe with telescopes and so forth. Okay, now, even to this day, the mechanism of why we have this solar cycle is not actually completely understood. All we know is that there are several interacting cycles working with a kind of an interlocked resonance inside the sun, and collectively the term that's been applied to those is the solar dynamo. So that's what's responsible for this kind of cycling of activity on the surface of the sun. So we can measure the solar activity visually just by looking at the number of sunspots that are present. Of course, Otto, a couple of months ago when he did his presentation, he was talking about that quite a lot in terms of measuring the sunspots and looking at the sun through different emission lines and seeing what was coming out of the sun. But here are the last few cycles. And of course, at peak time, more sunspots, more magnetic emissions coming out of the sun. Some cycles are more active than others. And again, we predict that based on the mean daily number of observed sunspots. The next solar maximum, I'm glad you asked, the next solar maximum is due in July 2025. So it's building up to a crescendo at the moment. Okay, and so solar flares and geomagnetic storms and things of that nature are also more prevalent at the maximum. Okay, and the other thing that happens most often at maximum is auroras. Thank you, Dr. Ian Griffin. He did give me permission to use that. I didn't steal it. This is because we get, with more activity on the sun, we get increased ionization happening in the atmosphere, which changes the characteristics in sometimes unpredictable ways. Okay, so it alters the reflection and absorption of the ionosphere layers. During the day, we can have these sporadic random events occurring, leading to very unusual characteristics in the atmosphere, which are called sporadic E events, because they happen in the E layer of the atmosphere. That's why the E layer is the most interesting one. Because they happen to the E layer and they are sporadic, and because radio engineers have got great imagination, they call it sporadic E. There we go. Sporadic E events, what they actually do is they allow much higher frequencies than normal to bounce back off the atmosphere down to Earth. Okay, so instead of the shortwave band, which stops at 30 megahertz, if you remember, then you've got a big space and then you've got your radio, FM radio, 88, 100 megahertz, that kind of thing. Sometimes you can get very high frequencies up to VHF and higher that are normally absorbed or shoot straight through, bouncing back over great distances. So when a sporadic E event is happening, you may get into your car and tune up the FM band if you're actually like tuning with an old style knob rather than just like pressing a button for the different stations. And you might hear something coming in. There wasn't a station there last week. Who's that? And it's Triple J from Sydney. This has actually happened to me with a little pocket radio sitting on the floor in my living room. I turn on the radio, 107.7, Triple J from Sydney in Levin. Right? So this can happen with sporadic E propagation. So like the ionosphere, amateur radio enthusiasts tend to also get very excited when this happens. And they probably start shedding a few electrons as well. Okay. So looking at the mechanism of this a little bit more, multi-bounce propagation can happen with these sporadic events too. Now look at this. Okay, we've got a signal that comes up here, comes down, bounces off there, goes up, down, and then you can kind of get stuck between the F and the E layer for a while and then come down to Earth thousands of kilometers away. It can have several bounces. Multi-hop propagation from different layers. So it bounces, comes down, up, down, or else up, down. All of this kind of activity can happen. And it gives rise to, it's not reliable, so you can't count on it happening. But when it does happen, it's really interesting because you can hear things that you normally, and you can receive signals that you wouldn't normally receive. This has also happened with analog TV as well. There has happened where people have been tuning, you know, the old days when you have those little tuning dials on the TV, tune up the band, and suddenly there's a signal there. What's that? It's a TV channel from another country. And then just as quickly as it came on, it disappears again, never to be seen again. Okay, sporadic E clouds are responsible for that. They are clouds of ionized gases, unpredictable and sporadic. And they can reach levels of ionization 4, 5, even higher than normal sunspot peak. They can last from minutes to hours. The clouds can be tiny, like just 10 meters, or huge, hundreds of kilometers. They can get blown around by the wind up at high altitude as well. They're usually only 10 meters thick, and this is the mechanism of action, because what happens is the reflections occur because of sharp changes in the electron density. Right? So that acts like quite a mirror to those electrons, because the electrons, it's this cloud, it's only 10 meters thick. Okay? It's another one of those, how do they form? We don't know. What causes it? We don't know. We've observed that there's a correlation between that and auroral activity, but is that a correlation? Is that a cause? We don't know. Okay, so now let's talk about the solar flares that happen on the sun. So a solar flare is a huge explosion on the surface of the sun. So when the sun is at a high peak of solar activity, you've got all these magnetic fields on the sun twisting and rotating around each other, much like if you take a rubber band and you twist it between your fingers and you pull it tighter and tighter and tighter, and then eventually the rubber band snaps and goes ping, and there's a release of energy, and the rubber band flies across the room as it releases all that coiled up energy. That's exactly what solar flares do. These magnetic fields twist around each other, ionized gas and plasma, until they stretch too tight and release. And when they do, they emit huge bursts of radiation in X-rays, ultraviolet, light, and radio. And they occur most frequently at times of sunspot maximum. Okay. The next thing is we have coronal mass ejections. So that's a release of magnetized plasma from the sun. It often follows a solar flare. You'll then get a coronal mass ejection from the sun. Okay, and what happens is the plasma that comes off the sun is then released into the solar wind, and it makes its way out into the solar system. When that, if it comes towards Earth, when it interacts with the Earth's atmosphere, you'll get the potential for a geomagnetic storm. Okay, a geomagnetic storm is just a disturbance of the Earth's magnetic field. This is dramatically not to scale, by the way. The sun's not this close to the Earth. Okay, so don't worry, we're not going to have the apocalypse here. Okay, but what happens is it's caused by solar wind or shockwave or a cloud of magnetic field from a coronal mass ejection. In any case, we have this outside force that perturbs Earth's magnetic field. Now, magnetism and electricity are related. Okay, so when you've got magnetism happening, you will also have electrical charge happening. So it disturbs the ionosphere in a similar way, but much stronger than high sunspot activity. They can be extremely intense. They can carry an immense amount of energy. And what that does is it electrically charges the atmosphere. Now, when these things happen, they can actually have quite devastating effects on our technology. Okay, so I've got a few examples of events that have occurred to our technology on Earth as a result of what's happening on the sun. In August 1972, there was an event in North Vietnam with sea mines, which are, the way sea mines work is they are magnetically triggered when a ship goes over them. Okay, so what happened was some flares and solar storms with, in fact, the fastest coronal mass ejection ever recorded. They destroyed a satellite completely in orbit because they hit that. And then it set off a few Navy sea mines in North Vietnam, because the sea mines thought that that magnetic influence was a ship going over, so boom. The earliest ever recorded coronal mass ejection was in 1859. It started fires on telegraph lines, apparently, and also delivered electric shocks to the poor Morse code operators who were tapping the Morse code keys. In March 1989, we had a geomagnetic storm, which induced a big electrical power blackout, and 6 million people in Quebec were without power for about 9 hours. I tried to get the power grid back online, just because of the electrical charges that were induced on the power wires by that activity happening on the sun. And in fact, if they go off in the right direction, solar flares can be detected by the Voyager probes. So you know how far away those are. Those are actually outside the solar system now. They can still detect solar flares happening if the cloud of charged particles happens to go in that direction. So these things carry an enormous amount of energy. So finishing off then, these things are just another natural disaster, but they come from space. So courtesy of the New Zealand Get Ready government website, this is just another thing you need to prepare for, along with floods and earthquakes and tsunamis and all that other stuff. So somewhere in your house, you'll have a solar flare and solar emergency disaster kit, I'm sure. And finally, I was going to talk about, I said I was going to bring in some exhibits. I mentioned earlier on that we had, there was this hobby, the shortwave listening, the nerdiest hobby in the world, or at least a contender for it. Just a little bit more about that. So this world map comes from the ITU, International Telecommunications Union. It's administered by the United Nations, and it's divided the world up into 85 zones. And there are actually competitions based on collecting these. Remember, I talked about these verification report cards that you can get from radio stations? There are actually awards that you can get from ITU, depending on how many of these zones in the world you've collected verification cards from over what period of time. So tell me a hobby more nerdy than that. So what I've done is I've brought in my collection of radio confirmation cards, which are just scattered on the table there. They look like postcards, but if you turn them over, you'll see there's all the technical information on them. They're from when I was most active in this hobby, 1985, 86. And I've got 30 countries, I counted, and 16 of the regions from this ITU map. And you've got to be a little bit careful because Radio Australia, for example, they've got a transmitter at Cardigan and Shepton, which is actually 2 zones. So it's where the transmitter is, not where the studio is, that it works on. And there's some references for you as well, which, oh, there we go. The animation has confounded me, but there we go. There's some references for you, which has got some backup information from stuff that I've shown you tonight. So yeah, that's what I have for you. So feel free to have a look through the collection of radio cards as you go and get your cup of coffee. Go on.